Welcome back. You got to put down your little screen to pick up your big screen so that you can do work and reward yourself with a little screen later, or maybe even a really big screen later. So logistics, just as we're kind of loading up and thinking about what's going on, we have homework number 3 due next week. And it seems like we're making progress, at least when I've been checking in on what's going on. It seems like we're steady progress towards submitting that. And then we have a couple of days to work on project 3. Should be easy, no big deal. It's just a little rocket science. Everyone says that one's easy. And then we'll be off into the last module. Like once we get homework 3, project 3 done, there's only one homework and one project left as far as like what's required for the class. And then from there, if you want to work on extra credit work, there's another module that kind of combines some of the work that we're doing now and some of the work in module 4, because it's a combination of like linear algebra and differential equations called boundary value problems, like but partial differential equations. I always thought partial differential equations sounded easier than ordinary differential equations, but it's very much the opposite. The ordinary ones are much easier to solve than the partial ones. They end up with all these infinite sums of all sorts of stuff. Maybe it's just me. That's like someone pointed out to me, like basic science, people are constantly struggling to get funding for basic science. And they started asking people, like, why don't you want to put money into basic science? And people were telling them, like, well, if it's so basic, then isn't it already done? Like, don't we already know everything we need to know? It's like, well, we just need a rebranding on basic science. It's not basic, it's not simple, it's like fundamental. Like, how does the world work kind of questions. That's how I feel about ODEs and PDEs. It needs a rebranding, really. Anyway. Anything cool or weird happening in homework 3? Or like some concepts that you might want to talk about or listen to? Is there anything like unexpected? You're like, why is this happening? Why does this work? I feel like a lot of numerical methods don't seem like they should work, but they work really well. Of like, just define the function, even if you know nothing about the answer, and then let the computer find the answer for you. It's like, wait, what? How does that? If I don't know the answer, how am I supposed to get to the answer? There's all sorts of cool methods to get there. I'll check in and see at least where we're at. See where we might need, or what might help for discussion or demo. Yeah. Which part are you working on? Okay, that's fine. Yeah. Okay. Yeah. So you can use like indexing to do it. Yeah. But it's gonna give you the same result. Yeah. Yeah. And diff is not like an actual differentiation. It is just taking nearest neighbors and subtracting them. Yeah, just doing that. Yeah, some people look at it and think like, isn't this negatively derivative? And like, no, 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 it's very much like, just take this minus that. Hi, how's it going? Yeah, well, that it's supposed to be beta now. So I had it right down. No, because you're integrating with so beta. So what we have right now is two first order differential change beta is change negative change and we want to multiply that times that delta do that loss. cool. So we're starting to look at some stuff down. So we're starting to look at like this pendulum problem where we know theta double dot is like a negative g over L sine theta for that pendulum, that is the differential equation for a pendulum. And then I want to integrate it. And so what I would expect is something like a spring, where it's going to start at some angle, swing to the negative of that angle, then come back to same original angle. Because I'm not saying that there's any kind of like damping or friction involved. I like to always double check that my derivative function is returning derivatives that I would expect. So like if I'm at pi over 2 radians, 90 degrees, then I should see that it accelerates down at like 1g of acceleration, because it's sine of pi over 2 times negative g over 1. And that is what I get, that as it catches up with me. 0, negative 9.81. So derivative of my angle and my angular velocity are 0 radians per second and 9.81 radians per second squared. So now let's just take like the exact same stuff that we were doing with fall drag and copy it down into my pendulum, ignoring all the lessons that we learned in the reading. So I don't need a state lacrosse. I'm just gonna have one like state. So just calling it that state. My right-hand side is not going to be fall drag. It's going to be my pendulum equation. And my state 0 is going to be that pi over 6. I think it's pi over 6. Yeah. So 30 degrees and then moving at 0 radians per second. And just going 0 to 6 seconds. I didn't find the natural frequency and then divide by that to actually get one period of oscillation. But time is just an independent parameter. I can make it as big or as small as I want. 0 to 6, but let's do like 31 steps. No errors. And this is just a quick check, like, am I getting the results that I would expect? If you just plot state, it'll show you both states, so my angle and my angular velocity. And I do get something, so I'm not getting errors. But is this what you would expect for the angle of a pendulum swinging? Blue curve is my angle, red curve is my angular velocity. Is this what we would expect? Has this ever happened in your grandfather clock? You go to start the pendulum, and like, darn, I have an infinite energy reservoir that's spinning the pendulum up and around to 2 pi radians to 25 radians, so 25 over 3. Like, it did 4 or 5 rotations to get there. So something's weird here. So let's just look at the angle to start. So we'll say t all rows in the first one. It's starting at 30 degrees. And here, let's do, I like degrees, times 180 over. I do all my math in radians. Like, it's always better to use radians. I know calculators have a degree mode, but really it's taking your degrees and multiplying by pi, dividing by 180, and then doing the math for you. So it's better to just stick to radians. So I'm going from 30 degrees, swing down to negative, I don't know, 50, and then it shoots off. This would be great if this was real, but it's not real. This is not a real solution. And we know that because if we look at like double the number of time steps, so right now we're going up to 1500 degrees, double the time steps, now I go to 500 degrees. So there's something wrong with this solution. Do you know what's wrong about it? This one, the reading does have the answer, but I'm wondering what you think is wrong. I'll let you think about it. But as far as like integrating the equation, it's always the same process. We can drop in any integration method that we want. You can define it however you want, as long as it's always taking like some kind of state, the derivative of the state, and then multiply by some dt step. And we can get better approximations. Right now I'm using Euler, but there's other methods that we can use too. So why is that Euler method giving me this like infinite energy generator pendulum? Like, it just keeps adding energy to this. It keeps moving faster and getting bigger and bigger angles. What's happening? Yeah. We have the pendulum. Should be pretty boring, right? But you always have like your acceleration equal to a negative number of times the angle. So the bigger the angle, the more it wants to go back to zero. Right. Yeah. Okay. So for those, usually like a sine or a cosine, some kind of bouncing, goes up, comes down, goes up, comes down. At least that's what it should be, and that's what we see. Like, I take the pendulum, bring it to 30 degrees, and let go. It should be 30, back to 30, 30. Maybe even keep decreasing, like add friction or drag or something like move energy. There's nothing to cause. Oh, right. Yeah, right. Up and around. Something weird with this one. Yeah, I mean, it does have to do with that time and like our time step. So the smaller the time step, we already saw. We made it smaller. It was slightly better of a bad approximation. Right. Yeah. When what's 90? Yeah. With this one, well, this one, oh, this like number here is just taking radians and turning them into degrees. So I can look at how many degrees it rotated. So right now, 360 is after 5.5 seconds, it went from bouncing back and forth to like all the way up and around. That's a little weird, right? Not usually what happens with a pendulum. At least none of the pendulums that I have. It has gravity in there. So if you think about like, this is the solution that we would expect, is that it's some kind of like cosine times 30 degrees. When we take this, so when we're like trying to integrate this differential equation, we're taking this whole thing and splitting it up into all of these like discrete spots. So I'm not saying like I want a function. What is the function of time? I'm saying like, all right, this, if I give you theta and theta dot, give me the derivatives, and then I'm gonna get another version of theta and theta dot, like one time step later. So if I'm starting here at that black point for my like initial condition, and I take the slope, multiply by time, then I end up, a slope of 0 ends up here. So already I'm starting off not great. I did not get any of that downward like cosine value. Now I take the slope here and I end up down there, and I'm a little bit worse. Then I take the slope here, end up down here. And with this Euler step, because we have that like delta t convergence and there's no checks, so there's this is an explicit method where it's just, no matter what, it's just going to march forward in time. It's never checking to see like, did I get to a value that makes sense or is converged. So I'm just going to keep getting worse, and because I keep using that slope and I'm not checking, this explicit method is just going to keep growing. And I can, if I keep making the time steps small enough, then I reduce that error. But there are other methods. Like we have other methods that work better. But roughly that's what we're seeing here. So if you're stubborn enough and you're like Euler method for life, like Euler is tattooed, you have like the Euler e to the I pi equals -1 tattooed on your forearm. So yeah, we can get Euler to work. Just say like 60,000 time steps, and sure enough, we get like a cosine plot. Bigger is better, right? Just with enough time steps, you'll get there. Or we could jump in and say, Well, I remember from the reading that there were like some other methods that seem to work better for oscillating things. Let's see. There's Euler step. I know I'm scrolling up and down, but like Hune step. So this is the magic of the Hune step. I zoom in some. So right at the top of the right at the top of those hashtags, it says next state is right hand side times dt, and that's exactly what Euler step, like the Euler step, does. What we can do with an implicit method is create a loop and keep checking. Like, don't move on to the next. Don't give a next state until we reach some kind of convergence. Like, create an error and decrease that error until it hits some specified value, and then give the next state. So we create like a next state old, which is just the same thing that Euler step would give us. Update that next step with like an average of right hand side of the state plus the right hand side of the next state, and then figure out what the error is. And as that error hits some kind of tolerance, like at some point it'll be the same value, like next state and old next state will be the same, so their derivatives will be the same, and then we finally return that next state. So now we've got like an implicit integration where it doesn't move on to time step 2 until time step 1 at least hits some kind of convergence. So if I do that, copy that in, then I could take out this thing and call it that Hune step. And now I don't need 60,000 steps. Go back to like 61 again. Even with 61 steps, I get the same plot that I had for 6,000 steps, 6001. So again, if you're Euler for life, it's fine. Euler works. It is the textbook solution for integrating numerical methods, but there's other things. There's a bigger world out there. The Runge-Kutta methods. This is one of many Runge-Kutta methods, which are like now that's like the default integration methods are either Runge-Kutta 2-3, like using 2 points with third order convergence, or 4-5, like fifth order convergence. So you need a lot less divisions in time to get to the same answers. Yeah.
So you increase the time steps, but you just kind of guess at 6,000.
That was a guess. Yeah, okay. I knew if it's huge, then it's gonna be the right answer. How huge is huge enough is that's that right. One's that one I could figure it out, or I can guess and check and just visually figure it out. Yeah.
Would it show a big difference, like the Hune set with less steps versus like in terms of time? Would it time? Would it show?
Oh, like how much time it took?
Like the 60,000 and the Euler versus just 60.
Yeah. So with that Hune step, it was 25 milliseconds versus Euler is now almost a microsecond. So like, what is that? 10? No, at least. Trying to get the order of magnitude right. 900 over 25. 36 times faster just by changing that integration method. And then the answer is exactly like we're getting the same answers for a given point in time. The angle is a given angle. Like getting all those extra data points along the way, or it's probably not giving us much extra information. And the really fancy like integration methods, they have varying time steps. So if the slope is not changing a lot, then make big time steps. And then as it starts changing more, make smaller time steps. And then if you want anything in between, you interpolate. So then you get a nice like smooth answer even with only 5 or 6 integration points. Those are like pretty nice. Like Julia has a nice like the programming language, Julia, not the person. I don't know if Julia is based on a person, a programming language. I don't know. Julia Stiles, like 10 things you hate about me or something.
Yeah. Did you get it? No. Think so it should be green.
Right now, you know, U64 track. Okay. Yeah. You want to meet like in person? Yeah, it gives a link, but yeah. 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 I mean, part of it is just like identifying how simple can you be, but still get the result that you want. Yeah. You're just right. You know, it's a solution.
No, for real?
Yeah.
Oh, crap.
And they're either way too complicated or so.
How did you do it? I think I got the first question entirely right. They can't read the protocol.
Yeah,
Oh,
well,
that's
they need-
right. And on the second question, that first part just completely threw me off.
exactly.
And then I just tried to skip.
Yeah.
Exactly what I mean. I couldn't do the first part.
Yeah.
And then, after the next part, the next part, the other. I can't get it. I was just like, okay.
I think the second part, I really didn't know what I was asking for. Nobody did that second question. Very dry.
Yeah, I just was asking for a grade. I don't think that I
Well, apparently it was just asking for extra two.
Yeah.
Like it wanted to just solve for X.
Where is
It's in the midterm and final samples.
Oh.
All at the bottom.
okay. You just added that. That was quick.
I guess he was just asking for X. Just solve for X. but that's definitely not what I wrote there.
Oh, wow.
And then yeah, part C, like I wrote down something on those, but it wasn't on the others. So
I think the main thing is sort of let's say the model works. What is the number that sometimes it's stuff like stress or being or something. And some of those simpler but still happening.
did you say parallel or did you say series? Yeah, I said parallel. That's good. He tried to throw us off.
Yeah.
You know, like after a student, but he was in class. He was like, you guys know these are things. Like, it's like they're not parallel.
Maybe
But
It's parallel.
it was parallel.
The only reason I put parallel is because I thought K1 was horizontal with the mass,
Yeah.
and then today I think it was K2 was the longest one was the vertical mass, but today the difference was almost the same.
Yeah.
So like motion was almost within the same parameters. I thought it was parallel.
I was just thinking about it, like the series means like usually means like one immediately the other one.
Yeah.
And then the match is then here. So like whenever they're separate from each other, they're parallel. And like even if like we could say like the two angles were zero, then it would be in series. They would be in series like that. But like the angle's not zero, clearly. So like they should be parallel.
I honestly, not gonna lie, I was like 50-50 on that.
Yeah.
Then I wrote it out on paper,
Yeah.
and I was like, yeah, it's horizontal. The other one was like vertical mass.
Yeah. Well, I was pretty pumped on that. I was hoping that it was parallel because it was a series that you have to do that. I did not study that enough. But
and if you know that
I don't even
yeah,
know.
as soon as he said that, where he's like, it's not parallel, and like it is, but the strings are parallel. Like that threw me off for sure. I almost did that.
I didn't really hear him say that. I was really not paying attention.
Yeah.
frequency squared.
Yeah, I just heard that at the time when I got to just like, especially because that the first part just isn't really
I think for the most part,
so I got probably 6%.
I don't get it.
Really?
Number one, looking at it,
Did you do cosine squared?
I didn't do cosine squared. That's what caught me.
Yeah, that I was lucky because I literally talked to the professor about that. Like the first thing was homework. It wasn't the prep homework, but it was homework one. Yeah. The similar example where it was like k times open parentheses then to plus x cosine theta, close parentheses, and then times cosine theta again. And I was like, why is it cosine squared? And he like he literally taught me.
and that's why it's so long.
But yeah, that it was kind of like the first question of homework. That's the only reason I was like if it was a completely random system that I didn't have anything like that wasn't in homeworks at all, I would have struggled with that.
Yeah, I think where I messed up everything else looks identical.
Yeah.
Of those times.
Yeah, I'm sure you won't take off too much for that. It's just
And then
Oh, time flies.
for the most part,
The weekend is here. Any last second errors, questions? All right, signing off.